welcome to the deep dive. Today we're looking at something, well, pretty mind-blowing. Full-color radio images of supermassive black holes.
Right. It sounds a bit sci-fi, but astronomers are actually using different radio frequencies, almost like red, green, and blue light.
To see these incredible objects in a completely new way.
Exactly. The Event Horizon Telescope team, the EHT folks who are leading this, the goal is to really understand the super energetic environments right around black holes.
Yeah, and we've got some great material on this new imaging technique. So our mission today, let's try and get our heads around what this color view of the radio sky actually reveals about black holes. Especially for, anyone wanting the big picture.
Let's do it.
Okay, first things first. Color with radio waves. How does that even work? It's not like visible light, is it?
No, not directly, but it's a useful analogy. You know how with light, longer wavelengths are red, shorter are blue? Well, in radio astronomy, we can treat different frequency bands like color channels. Think of lower frequencies, longer wavelengths as maybe red, and higher frequencies, the shorter wavelengths, as blue.
Ah, okay. So the telescopes are picking up these different radio frequencies.
Precisely. They grab data in specific narrow frequency bands. Then, by sort of layering this data, like in Photoshop, they create these composite images.
And the colors show what exactly?
They highlight differences in structure and the energy of the plasma swirling around the black hole, maybe even temperature variations. It emphasizes features you might miss otherwise.
Got it. But I remember reading that our own atmosphere is a real pain for radio astronomy, right?
Yeah.
Especially for those finer details.
Whoa, absolutely. It's a huge challenge. The water vapor, other stuff, it distorts the incoming radio waves. It gets particularly bad at the shorter, like 1 millimeter wavelength.
Which are the ones you need for the sharpest images.
Exactly. It's like looking through shimmering heat haze, blurs everything.
So how do they tackle that? How do you correct for that atmospheric shimmer?
This is where a really clever technique called frequency phase transfer, or FPT, comes in. It's quite neat.
FPT, folks.
What they do is they continuously watch the source at a longer, more stable wavelength, say 3 millimeters, where the atmosphere causes less trouble.
Okay.
By seeing how the atmosphere affects that signal in real time, they can figure out the distortion and then apply corrections to the data they're simultaneously collecting at the more sensitive 1 millimeter wavelength.
Wow. So you use the stable signal to fix the wobbly one. That sounds a bit like those laser guide stars optical telescopes use.
That's a great comparison. It's the same principle, essentially creating an artificial reference to subtract the atmospheric blurring.
Brilliant. Now, the sources also stress that doing these multi-band observations at the same time is critical. Why simultaneity?
Right. That's key, because the stuff around a black hole, that accretion disk, the jets shooting out, it's not static, it's incredibly dynamic. Things change, and fast.
On what timescale? Hours? Minutes?
It can be hours, even faster sometimes. So if you observe at, say, 3 millimeters now and then switch to 1 millimeter an hour later.
The picture's already changed.
Exactly. You'd get this weird mismatched image, almost like ghosting. Things would appear smeared or in the wrong place relative to each other. Simultaneous observations give you a true snapshot across all the colors at one moment.
Okay, that makes complete sense. So this FPT, the simultaneous multi-frequency stuff, it's proof of concept now, but where's it heading?
Well, this really opens the door. It's paving the way for things like the next generation EHT, NEHT, and another concept called the Black Hole Explorer, or BHEX.
Better telescopes, basically.
Much better. With advanced receivers designed specifically for multi-frequency work and even better FPT capabilities. The really exciting prospect they talk about, live, full-color black hole movies.
Hold on. Live movies of a black hole environment.
That's the dream. Imagine actually watching these regions evolve over time in multiple radio colors.
What could we even learn from that? I mean, what are the big questions those movies could answer?
Oh, huge questions. We could potentially see jets forming and launching in real time. Watch how magnetic fields twist and reconnect, releasing energy. We could test gravity in ways we just can't right now. See if Einstein's ideas hold up under those extreme conditions, or if something new appears.
Seeing general relativity in action, or maybe its limits. And what about the colors themselves? What can the different hues tell us about the accretion disk, the stuff falling in?
Great question. The colors could map out temperature gradients across the disk, show where the plasma is densest, maybe even trace the composition of the material spiraling inwards. How does it heat up? Where do the magnetic fields dominate?
And the jets, these enormous outflows. How does color help there?
Well, you could see the structure within the jet in different colors, which relates to the energy of the particles and the magnetic field strength along the jet. This helps us figure out how they're accelerated, how they're shaped, and ultimately how these jets impact the entire galaxy they live in.
Right, linking the black hole to the whole galaxy's evolution.
Yeah.
And you mentioned magnetic reconnection, those sudden flares. Could we see those happen live, in color?
That's definitely a key target. Can we capture these transient energetic events as they unfold? Seeing them in multiple frequencies simultaneously would give us massive clues about the physics driving them, what triggers them, how does the energy release.
So wrapping this up then, we're essentially adding a new dimension, color, to radio observations of black holes.
Exactly. It lets us see their structure and dynamics in much richer detail, overcoming the atmospheric blurring and capturing changes as they happen.
It's a much more vivid and dynamic picture than ever before.
Absolutely. Moving beyond static images to something much closer to seeing the real thing.
Which leads to a really fascinating final thought. Just imagine truly watching these incredibly enigmatic objects flicker, shift, and flare in living color across the radio spectrum. What completely unexpected things might we see? What new physics might reveal itself when we have these cosmic movies running? That's something to ponder. Thanks for taking this deep dive with us.